This is the first lecture for the course MAT291, and lecture 1 is divided into 3 modules, or 4 modules, that is 1A, 1B, 1C, and 1D. Module 1A is review of vectors, and typically the first 2 slides give you general information about the presentation to follow. The first slide just summarizes where this material is coming from, including the objectives of this teaching module. And the second slide will be just a review of the different slides contained within this teaching module. I'll just go over that slide very quickly. It's for your reference only, and then we'll move on to slide 3. So for lecture 1A, we were dealing with a review of vectors, which is from last year. And this material you can find in sections 1 to 3 and 6 of Reading Assignment 0. Note 1, sections 1 to 3 of Reading Assignment 0 are a review of your math courses from last year. And note 2 is section 6 of Reading Assignment 0 discusses the difference between position vectors and general vector fields. This material will be introduced again starting at lecture 6. And the last note here is that section 7 of Reading Assignment 0 is for your interest, but you do not have to read it. This course in itself is quite demanding and quite dense, and so you may want to skip it for now. So the objectives of this teaching module are just a review of vector properties and operations performed on vectors. Okay, so this is the outline I discussed. You can just briefly pause the video if you'd like to look at them, but I'll just move on from here. All right, so first we'll discuss scalars, scalar fields, and the difference between the two. Pseudoscalars, which I'm sure you haven't heard before. Maybe the term was introduced to you last year, but here I basically give you a little bit more information as what we imply by the word pseudoscalar. And of course, combination of scalars and pseudoscalars would turn out to be complex numbers. So what are scalars? They're numbers which span the real number set. So from minus infinity to positive infinity. Scalar fields in 2D just means we can assign a scalar value to a given point. And so for instance, if you want to know the mass of a point mass, you just assign a value to it. It's a scalar value. You can also assign something to points on a line. So that would be mass per unit length at each point on a line. Or to points on an area, which would be mass per unit area. So you're assigning a mass per unit area to specific points on an area. We can extend this also to 3D, in which case everything looks similar. That is, you can assign a scalar value to a point, to points on a line, to points on an area, but also to points within a volume. So for instance, you could assign a mass per unit volume to a specific point within a volume. All right, what are pseudoscalars? So let's demonstrate essentially how we arrive with the notion of a pseudoscalar. So I've basically included here the equation x squared plus 1 equals 0, which is a quadratic equation. And the objective is to solve for x. When I solve for x, I end up with 2 solutions, plus or minus square root of minus 1. Well, square root of minus 1 has no meaning. I mean, it certainly is not a real number. And so the fact that it exists means that we have to give it a label. So we define a label j. Sometimes they also use I. And this basically will define as an imaginary number. So given that we now have a definition for square root of negative 1, what do we get if we try to solve the quadratic equation x squared equals minus a squared? If you solve this quadratic equation, you'll get x equals plus or minus j times a. So this is an imaginary number, basically scaled by a value of a. If we now take combinations of imaginary numbers and real numbers, and so for example, consider the solution to the equation, the quadratic equation, x squared plus 2x plus 2 equals 0. If you solve this quadratic equation, you get 2 solutions. You get one solution which is x equals minus 1 plus j, and a second solution which is x equals -1 minus j. So you'll notice here that the solution consists of a real number and an imaginary. So here's your real number and here's your imaginary number. We refer to this combination of real and imaginary as a complex number. So the question is, how do you visualize a complex number? Because you have two degrees of freedom, a real number and imaginary number. So we create this duple, which is this ordered pair, A representing the real component and BJ representing the imaginary component. We can graph it on an XY plot, but now the y-axis represents the imaginary component of the complex number. So this now becomes the j-axis rather than the y-axis. And the x-axis, which is along the x-axis, represents the real component of the complex number. So this now is not the xy plane, but the xj plane, and it's referred to as the complex plane. So if I want to graph 2 plus j3, then basically the duple would have the real number for 2 and j3 for the imaginary component, and this is where that point would lie on the complex plane or xj plane. Complex number analysis is a subject of the course MAT290, which you will be also taking concurrently this term. All right, so now let's look at the difference between position vectors and vector fields. And I'm only going to be using 2D illustrations because it's simpler to visualize, but 3D is also possible. It's just that it would be unmanageable to draw things on the page. So first of all, I'd like to provide a definition. A position vector also is called a polar vector. And a polar vector just implies that you're using a reference point as an origin, and so the tail of the vector is always anchored to the origin. And the vector basically will have a direction as well as a length. So for example here, I can write it in this form. These basically are angled brackets to represent vector notation. So this is the x component and the y component. And if you were to graph it, you would find you end up with a vector that looks like that. But typically we'd like to take this and recast it in terms of a vector, which is a unit vector and a magnitude of the vector. And so this vector is equivalent to this vector, but you can clearly see here that if you were to take the norm or the magnitude of this vector, you'll get 1, which means by definition it's a unit vector. And the value that sits outside the unit vector, which is a scalar, this is just the magnitude of that vector. So we'll be using this type of vector formalism quite frequently because the unit vector basically gives us specific information only about direction. And this is very useful to know. All right, so what about a vector field in 2D? Well, there are 3 different cases I'm considering here. So for instance, here's an example where you have a vector located with its tail at position 1, 2, and this is basically the orientation of the vector. Here it's designated as 1, -1. The fact that this vector is lying at some position in space on the xy plane makes it a vector field. And this is just an isolated point. So there's a vector at this position pointing in this direction. But we can also have a vector that's along a line. So for example, here you have a series of vectors tail to head, all connected to each other, going from here to here. So you might ask yourself a question, so under what circumstances from a practical standpoint does this have any relevance? Well, for example, let's say a train is moving along a train track in this direction. At any given point in time, we have 2 pieces of information. We know the train is moving at a certain velocity, which we call its magnitude, and we know it's moving in a certain direction. And that direction we'll describe in terms of a unit vector. So this would be a vector field because it's a function of position. We'll be discussing vector fields later in the course, but for now, try just to get a visual understanding of what a vector field is. Well, we can also look at a 2D vector field. So this is an example where we have a position-independent vector field. So you'll notice here all the vectors are all pointing in the same direction, and their magnitudes, which typically are taken to be their lengths, are everywhere the same for this example, but they basically are everywhere pointing in the same direction for every position xy. In contrast, if you look here, depending on where you are located, the vector field is pointing in a different direction. So this is a case of a vector field which is position dependent. You can basically redraw these pictures for 3D if you wish, but again, this is just going to make the picture complicated. So let me come back then to the definition here, polar vectors. How do we know if it's a polar vector? Well, or for that matter, a vector field. It changes polarity if the signs of the vector components are negated. All right, so for example, if you look here, if I made this negative and I made this negative, this vector would basically flip direction, change polarity. So in this case, we're dealing with a vector field, which we call a vector which is polar vector. All right, so next we'll look at our basis vectors, and there are various types of basis vectors, followed by operations performed on vectors. So if we look at the pictures to the left, let's look at this. We have basis vectors. Basis vectors, basically if you take a linear combination of any two basis vectors, you can generate any vector you want in this example in 2D space. But there are special types of basis vectors which are particularly useful. One are the orthogonal basis vectors, which are orthogonal to each other. In this case, it's sort of clear that we're going to use the direction along the x-axis as one basis vector and the direction on the y-axis another vector. Now, if we basically all consider also these going to be unit vectors, then we would say this is orthonormal basis vectors. And generally, when you see x hat and y hat it, right, then you're basically dealing with orthonormal basis vectors. So if I'm looking at an arbitrary vector here, then this will be a linear combination of this basis vector and this basis vector. And that's basically what you see here. Now this hat should be over top, but the software basically didn't let me do it. All right, so anything with a hat base is taken typically to be a orthonormal basis vector. All right, well, what about in 3D? What would change? Well, we would have a third basis vector. And again, because it's orthonormal means it would be perpendicular to both x hat and y hat. And again, you'd end up with a linear combination of the three basis vectors. All right, so that's more or less a quick review of the essential aspects of vectors. And so now let's look at operations that we can perform on vectors. So first of all, let's look at what we call the dot product or inner product. And so what does this imply? It means if you take a vector, you do the dot operation on it with another vector, then the resultant of this dot product is a scalar. So it takes two vectors and produces a scalar. And so this picture here is giving you the two vectors, v1 and v2. Here I've shown them to be on the xy plane for convenience. And I'm showing the angle theta, which we'll refer to shortly, which starts at v1 and moves in the direction of v2. Now these directions are all going to become important when we discuss what we mean by right-handed coordinate systems. But for now, this is basically how we're measuring theta. So in a counterclockwise direction with respect to the xy plane. And then of course we have our basis vectors, the x hat vector and the y hat vector. So when we do a dot product, it means we take this vector and dot with the second vector. That's this product, this operation. Then what we're doing is multiplying the first component of the v1 vector with the first component of the v2 vector, which means the two x components are multiplied. You do likewise and make a product between v1y and v2y, and likewise you make a product between v1z and v2z. And you take those three products and add them together. This is the resultant, and this of course is a scalar. You can also write it in alternative form, which is if you take the magnitude of the vector v1, multiply by the magnitude of the vector v2, and multiply by the cosine of the angle between these two vectors here, right? Then these two are equivalent. So for example, if you're interested in knowing what the angle between these two vectors is, you can perform this calculation. You can certainly perform this calculation and this calculation, whereby you can now compute what cosine theta is, from which you can determine the angle between the two vectors. Okay, what about the properties of an inner product or dot product? Well, it's commutative. So that means we can swap the order of V1, V2, and the resultant answer is still the same. Okay, it doesn't matter. One other property is this V1's perpendicular V2, then the dot product is equal to 0. We'll make use of this property very frequently in all the vector analysis calculations that we'll be doing henceforth. All right, so last year you were introduced to this thing called a cross product of two vectors. Well, we're going to call it a pseudo-vector, but also it's given the name axial vector, and I'll explain why shortly. But the cross product is defined in 3D space, not in 2D space. On the other hand, we can sort of fake it. We can actually make a cross product work for us in 2D if we basically set the z components of the two vectors that we're going to be operating on to 0. We'll come to that shortly, but I'm just saying that there are always ways of twisting things to make things work for you. All right, so let me now give you the explanation as to why a cross product between two vectors is something called a pseudovector or axial vector. And properties of pseudovectors are invariant. They don't change polarity if the signs of the original vector components are negated. And we'll come to this in a second. This is just a formal definition, and we'll basically go through it by way of an illustration. So again, I have the diagram that we had before, but I've introduced now another vector, which is the resultant of taking the cross product between vector v1 and v2. And that's right here. Turns out that a cross product produces a third vector, which means it's an operation on two vectors that produces what looks like another vector, but we're going to call it a pseudovector. Again, explanation is coming. And that pseudovector is perpendicular or lies perpendicular with respect to the plane in which vectors v1 and v2 lie. All right, so you have a vector v1 here and a v2 here. So this angle theta that you see between these two vectors, here it's in the xy plane. But if these vectors are oriented in an arbitrary direction, then the angle theta is basically the angle taken in the plane which is shared by vectors v1, v2. This also applies to the case of the dot product that we looked at on the previous slide. So the angle theta is lying on a plane, and of course the plane's orientation will change as vectors v1 and v2's orientation change as well. But the main thing to know is if these two lie on a plane, then this vector is orthogonal to the plane in which these two vectors lie. So how do you compute a cross product? All right, well, first row, this is going to be a determinant that you basically are calculating. The first row includes the unit vectors or orthonormal basis vectors, x hat, y hat, z hat. The second row contains the vector components of the first vector, and the third row contains the vector components of the second vector. Now, if you compute the determinant of this matrix, and go back and review from last year how a determinant of a matrix is computed, then what we end up with is this component preceding the x hat vector, this preceding the y hat, and this preceding the z hat. Okay, so let's look at some properties. If I were to take the magnitude of the resultant, that is the cross product of v1, v2, then this is equivalent to the magnitude of vector v1 times the magnitude of vector v2 times the sine of the angle between the two vectors. This is almost the dual of a dot product. In one case you use cosine, whereas here you use sine. Also, as I mentioned, v1 and v2 are both perpendicular to the result of taking a cross product between v1 and v2. So if you look here, this vector and this vector are orthogonal with respect to each other. this vector and that vector are also orthogonal with respect to each other. Lastly, if V1 is parallel to V2, that means the angle between the two is 0, then V1 cross V2 is equal to 0. Now, if you flip the sign, like V1, V2, flip the order, V1, V2, change it to V2, V1, then these two are related to each other, but they're related to each other by a change in sign. So this has an anti-commutative property. All right, so now let's go back and try to understand, why this is a pseudovector, the resultant. And the simplest way to look at that is to look at the definition here. Right? If you change the signs, does the polarity of the vector, the resultant vector, change? Well, if you look here, if I change this sign and this sign, this remains positive. Similarly here in all these 6 terms, if I change all the signs, nothing has changed. So this resultant is a pseudovector, primarily because of basically the property of a pseudovector. Okay, so another spin on this one, in terms of why we call it a pseudovector, is when we look at this and try to imagine it in an equivalent 2D form. So as I mentioned earlier, we can take this cross product and make it work for us in 2D if we make the z component of vector v1 0 and the z component of vector v2 0. But in that case, we are presuming that vector v1 and v2 exist in 2-dimensional space, not 3-dimensional space. But the z vector, the z hat vector in 2D doesn't exist. And yet when we compute the cross product, which is the determinant of this matrix, we end up with this expression, a z hat. Well, how can that be? Well, the only way that can be if we decide to give this a new label, and I call this a ghost axis, which happens to be pointing in the z hat direction, but because z hat doesn't exist, I'm going to call it J, and I'll put it in bold, so that is represented basically as a pseudovector. So the J symbol in vector notation form is a pseudovector, and it's pointing out of the plane, which of course in 2D doesn't exist. That's why we call it imaginary. Okay, we're going to look at this in more detail in lecture 21. There's a lot of history surrounding vector calculus. I mean, dating back to about 140 years ago. There were 2 competing theories regarding how we should look at vector calculus. The simpler one won out at the time, but the one which was more thorough and basically covered higher dimensions in a much more intuitive way was abandoned, and only recently has it gained favor again. But again, you can still use the classical approach to vector calculus to solving most problems that you see today. It's laborious and difficult from an intuitive point of view to understand how to generalize to higher dimensions. Okay, so let's look at some other properties. Look, if we took the magnitude of this, what does this represent? It represents the area of a parallelogram. So the cross product is interesting because it's somehow tied to the geometry of a problem. Also, if you take a vector, a third vector now, v3, and dot product with the cross product, this turns out to be the volume of a parallelepiped, which sides which were defined by vectors v1, v2, and v3. So the use of vectors and operations on vectors can also be tied to the geometry, areas, volumes, and so on. So this is effectively a review of what you need to know going into this course. And so we've covered both vectors, pseudovectors, and the operations on vectors. This concludes first lecture, which is lecture 1A.